Ice tables are not clicking for me.
Ice tables are confusing.
Okay. It's just a way to organize here.
Yeah, I don't get it.
So today we're going to be going over 7.4, La Chatelier's principle. We did this in chemistry.
No.
Slightly. We did. Okay. If change is imposed on a system at equilibrium, so you're already at equilibrium and you have some kind of change. Yes, the scales, yes. The position of the equilibrium will shift in a direction that tends to reduce that change. So if, let's say I have an equation, A plus B yields C, okay, and let's say I add B to my system, okay? I like to use my hands. So when I teach this in chemistry, I use my hands. So if I add B, which side of the reaction is increasing? This one, okay? So in order to relieve that stress, and I think about it in terms of water flowing, which way does the water have to flow? Towards the products, which means my products are going to increase while this kind of comes down until they meet a new equilibrium. Does that make sense? Okay, so whatever side changes, so our AB increases because we added B, so that means we're going to shift towards the products, so we have to make more products. These are going to be consumed until they meet in the middle or meet at equilibrium again. Okay, what does this look like in terms of a graph? Okay, so we have already at equilibrium A plus B and C. Okay, so they're already at equilibrium. They're already straight lines. They're not changing anymore. Okay, we have an increase in AB. It's a sharp increase. Okay, so we're going to have a sharp increase. Okay, and basically what it has to do is it has to start to come back down while your products come back up. So your products, or AB, is going to start to come back down and level out. Your products are going to slowly increase and then level out again. Okay, so the sharp either dip or spike means that's what we've added to or taken away from. Because sometimes you could take away. So if I were to take away A and B, right, then we would shift reverse. So we're going to shift forward due to that change. So it's just easing the pressure or easing the imbalance. Okay, so concentration. The system shifts to relieve the stress. So if I were to add more SCN, which way am I going to go? I'm going to shift forward. Which means I'm going to produce more concentrations of products and my reactants are going to decrease. Okay, to relieve that stress. So because I increase my reactants, they're going to start to come down while the products come up until they level out again. Okay, if I add OH, which creates FeOH solid, what is this telling us? What is this removing? It's removing Fe because it's making it a solid, which means it's no longer part of the reaction. Okay, so since we add OH, it's going to take out some of my Fe, which means my reactants are going to go down. So which way am I going to shift? I'm going to shift reverse, right? Think about flow of water. The water's going to flow this way. So we're going to shift reverse. Okay, which means we're going to have an increase in our reactants, concentration of our reactants, a decrease in our concentration of products. Okay, if I pour water into the system, the concentration of all the species is going to decrease, right? But they're all going to decrease equally. So is there going to be any kind of shift? No. So it dilutes everything. Okay, so no shift. Okay. So consider the following equilibrium system and evaluate each stress to determine if the result in an increase or decrease in concentration of CrO4. So we're trying to figure out what's happening. Are we going to increase the concentration of that or decrease the concentration of that? Okay, so for the first part, we're having an addition of Cr2O7. So that's a reactant. So if we increase the reactants, which way are we going to shift? Forward. So are we going to make more CrO4 or less? If we shift forward, we're going to make more. Right?
Oh, that's on the other side.
Yes. So we're going to increase the concentration of CrO4. Okay. For the next one, the addition of OH ion that reacts with H3O plus to become H2O. Yes, so it's taking out this, right, because it's becoming a liquid, because it's reacting with the H3O plus to become a liquid. So that means we're decreasing the H3O plus, which means we're going to shift which direction? Forward. So we're removing H3O plus, which means we're going to shift forward. And just like before, because we're shifting forward, we're shifting towards the CrO4, so it is going to increase. I think I told you guys wrong on the one up above. For part C, concentrating the solution by allowing water to evaporate. Okay, this is similar to what I said up above, but it does change. I just read it wrong.
Which one?
The last box. We'll go back to it. But let's talk about this one. Okay, so for part C, we're allowing the water to evaporate, which means are we increasing the concentration or decreasing the concentration? We're increasing all of them. So let's write. So we have our CrO4 squared and H3O plus cubed over Cr2O7 to the first power. Okay, so what we did was the molarity of this increased, but we squared it. The molarity of this one increased, but we cubed it. This one we increased the molarity. Okay, it's just to the first power. So what happened to this number up top? Did it get really, really big or really, really small? Big, right? Because we're squaring this and we're cubing this. So this got really, really big. Okay? This didn't increase by much. So this increased by but not by much. So it's small, but not terribly small. So overall, my Q value is going to be greater than my K value because this increased by so much. So because Q is bigger than K, it means it went too far. So which direction? Reverse. Okay, so if we go reverse, we're shifting away from the Cr4, so my concentration is decreasing of my CrO4. Okay, let's talk about the one up above where it dilutes everything. Okay, for that one, our Q is FeSCN to the first power divided by Fe to the first power and SCN to the first power. Okay, all of them are decreasing. Okay, so this one got slightly smaller. Okay, and these got smaller by a lot. Very, very small. So if you take a number divided by a very small number, what happens to the overall number? Gets big, which means our Q is greater than K, so it will shift reverse. I forgot to plug it in. It's basically what I forgot So let's talk about, so that's what happens when we change concentration, how it shifts dependent on concentration. Okay, what happens if pressure is changed? So when the overall pressure of a system is increased, the equilibrium will shift to the side with less moles of gas. We're looking for gas whenever it's talking about pressure. Okay, so we're looking at what is it labeled in the balanced equation. We're looking at only the moles of gas. Okay, so the way to remember this, if you have high pressure, okay, so if you're under a lot of pressure, you're really, really stressed, okay, you want to be around less people. Okay, you're really, really stressed, you don't want to be around a lot of people. Okay, when you have really low pressure, meaning you're not stressed at all, you want to party. Okay, so this is just a way to remember which way you're going to shift depending on the pressure. So if you have more pressure, it's going to shift away from the side that has more gas. Okay, if it's less pressure, it's going to shift towards the side that has more moles of gas. Okay. The addition of an inert gas will have no effect on the equilibrium in the system because it's not actually changing anything. Okay, it's not interacting. And then changing the volume of the system affects pressure. So if we increase pressure, the volume decreases. So they're inversely related. Okay, so think about it. If you push pressure on a balloon, it's going to get smaller. Volume gets less. Okay, so for this one, we're increasing pressure. So you have high pressure. You want to go to the side with less people. Okay, let's count the number of moles of gas. How many moles of gas do I have on this side in total? 2 moles. How many moles of gas do I have on the product side? 1 mole. So if I have high pressure, I want to go towards the side with less moles of gas. Which way am I going to shift? Shift forward so more products would be made. Okay, for this one, I'm increasing volume. If I increase volume, what's happening to pressure? It's going to decrease because remember they're inverse. So we're decreasing pressure. So if we're decreasing pressure, we're going to go to the side that has more moles of gas. So let's count how many moles. How many moles of gas do I have on the reactant side? 3. How many do I have on the product side? 4. So which direction am I going to go? Forward. Okay, for this one, I'm increasing pressure. So I'm going to go towards the side that has less moles of gas. How many moles of gas do I have on the reactant side? 7. How many do I have on the product side? No. 0. Be careful of that. Okay, they come sometimes. A lot of times they throw in either solids or liquids. So again, we're looking only for gases. So which way are we going to shift? Forward. Okay, one thing to note. If you have equal number of moles of gas, pressure has no effect. Okay, so like if this one, if we had 4 and 4 moles, there would have been no shift because they're equal in moles. So pressure would have no effect on the overall reaction. Okay, so that's pressure. Okay, those 2 rules. High stress, less people. Low stress, party. Okay? All right. Last condition that shifts reactions is temperature. Okay? Temperature is the only thing that changes K. There are so many questions that you get that'll say, like, which of these conditions would change the value of K? The only thing that changes the value of K is temperature. Okay? So, we're going to treat energy as a component of the reaction, and then it's the same thing. We just move our hands and figure out which way it's going to flow. Okay? So, endothermic is positive enthalpy, the energy goes on the reactant side because it needs energy in order for the reaction to go. Exothermic, exit, heat is a product, so it is negative delta H, and it goes on the product side. Okay, so for our practice problem on this, determine the shift and how K is affected given the reaction, and it tells us we have positive enthalpy. So where is the enthalpy going to go in our reaction? Reactant side or product side? Reactant side, because it's positive enthalpy. So I'm going to put it on the reactant side. Okay, so if I raise the temperature, which direction am I going to shift? Forward. So it's going to shift forward. Okay, which means I'm increasing the amount of products, I'm decreasing the amount of reactants. Okay, we know that our K value is products over reactants. So if I make my products bigger, I'm making my reactants smaller, what's happening to the overall K? It's getting bigger. So K increases in this instance. Okay? So raise in temperature, it's going to increase because it is on the reactant side. Okay? For lower temperature, okay, if we drop the reactants because of the lower temperature, we're going to shift reverse. So we're shifting reverse, which means we're going away from products. So our reactants are going to increase. Our products are going to decrease. So again, when we're plugging them in, okay, our products got small. Our reactants got big. So you take a big or a small number and divide it by a big number. What's going to happen to the overall number? It's going to go down. So K will decrease in this situation.